we will discuss a topic of engineering mathematics here named as complex variable. Now, this is a topic which is related to complex numbers, definitely as the name suggests, but not of detail of complex numbers has been asked, as we have to basically discuss the calculus related to complex variable, that is the integration and differentiation of this particular complex numbers. We actually define something called as complex functions, right, which is functions of complex numbers basically. Let us talk about the weightage. If you talk about the gate paper, would be in gate it will be 0 to 2 marks. Sometimes you may not find a question on complex variables, but there could be question on 2 marks also, maybe 1 mark also could be there. It's not a rigid. I have taken an average, I have taken an average for so many years of teaching and get papers when you analyze complex variable, right? So when I talk about complex numbers, what comes to your mind when I talk about complex numbers? Complex numbers are, I come to my mind is something z of the x plus iota y, right? Where x is called as the real part, right? And y is called as the imaginary part, and sir iota is root of -1, right? This is what we have studied in your earlier standard also, right? I also know what is iota square. Iota square will be sir -1. What is iota power 4? Iota power 4 will be 1. What is iota cube? Iota cube will be minus iota, can I say? Yes, how? See, 1. What is iota cube? Iota cube will be minus iota, can I say? Yes, how? See, iota cube is iota square into iota. Iota square is -1, so it is -1 into iota, or you can say minus iota. Why I'm telling you these things, sir, is very important because in paper, very fundamental level questions sometimes are asked. I'll tell you how. Very fundamental level questions sometimes are asked on this, right? So we know about complex numbers, right? Now, if I talk about, they are represented on a complex plane, right? Let's say this is a complex number x plus iota y, right? This is your y axis, and this is your x axis, or we call it the real axis, and this is called as the imaginary axis. This is the imaginary axis, right? Now if I talk about this point, this is, let's say this is x plus iota y, the point. Now if you see what is this x plus iota y, if you want to understand this thing, you would say, sir, this and this. So this is x and this one is y. Now if I want to find this, let's say r, so can I say this is x square plus y square? It's a Pythagoras theorem, right? So you can say that r is nothing but x square plus y square under root. This r is nothing but the modulus, is nothing but the modulus or absolute value, absolute value of z, the complex number. You can say z modulus is under root of x square plus y square. So it is nothing but the distance from the origin. We can basically say it is nothing but the distance from origin. Distance from origin. Right? Clear? Next thing we don't understand is something called as argument of z, represented normally by theta. Now we can easily see, if I want to find this theta, So can I say it is nothing but tan theta? Tan theta in the diagram will become what? Perpendicular upon base y by x. But theta is nothing but tan inverse of y by x. For the complex number, theta or the argument is nothing but tan inverse of y by x. So we know all these things, right? We know how to add complex numbers, right? Simply if I say uh, addition of complex numbers, if I say, right, add complex numbers. Simple fundamental, if I say z1 is equals to x1 plus iota y1, and there is z2 which is, we know how to add complex numbers, right? From the origin we can basically upon base y by x, but theta is nothing but tan inverse of y by x. For the complex number, theta or the argument is nothing but tan inverse of y by x. So we know all these things, right? We know how to add complex numbers, right? Simply if I say uh, addition of complex numbers, if I say, right, add complex numbers. Simple fundamental, if I say z1 is equals to x1 plus iota y1, and there is z2 which is x2 plus iota y2. So if I want to do z1 plus z2 is nothing but x1 plus x2. Similarly, you can do other operations also, plus, minus, and all those types of stuff, right? Right. What we want to understand here is we want to understand functions of a complex number or a complex variable, which we call as complex functions, denoted by W. The functions in Z, where Z is x plus iota x plus iota. This can be also represented as W is equals to f of Z is equals to u of x comma y. This is a function in x comma y, and iota times v in x comma y. There can be another imaginary part and the real part of the complex function, right? What do I mean by this now? I mean to say that there is a function fz where z is a complex number and that is denoted by w. So there can be a function of z. Now function of z means what? A real part in x and y, or maybe third variable, and a imaginary part, because complex functions means what? It's the same thing. So this is w is nothing but the complex function. Clear? So we are actually here dealing with complex functions, the derivative of those particular, right? So when we're talking about the derivatives, right, the first thing we'll talk about derivative of a complex function. First thing we'll discuss is called as the derivative of a complex function. Now when we talk about the derivative of the complex function, we have to define every function do not have a derivative. You have to have some necessary and sufficient condition for a function fz to have a derivative. So what are the conditions? Those are basically called as Cauchy-Riemann conditions, right? Now, apart from Cauchy-Riemann condition, there have to be something which is a let us statement. We should take it a point. The necessary and sufficient conditions for the derivative of a function fz to exist for all values of z in a region R. First condition, del u by del x, del u by del y, del v by del x, del v by del y should be continuous. And second, del u by del x should be equal to del v by del y, and del u by del y should be equal to minus del v by del x. These are called as Cauchy, Riemann, these are name of scientist equations, or we call it CR equations in short form. Right? If these two things are valid, then you can definitely say that the function is differentiable. Then the function is differentiable. Clear? Now what do you want? Now this is the condition for differentiable. Now what is the f dash? We have just talked about conditions. Now if it is differentiable, then f dash z is nothing but del u by del x plus iota times del v by del x. This is basically f dash z. You can say then the derivative is defined as something like this. Clear? Right. Now there is one more term connected to this that is called as analytical function or analytic functions. Now what are analytic functions? Let us understand this. Any function which satisfy your CR conditions is called as analytic function. What about CR condition? Del u by del x should be equal to del v by del y, and del u by del y equal to minus del v by del x. If you satisfy, then it is a analytic function. Or you can other way around say any function which is a single valued function and is defined and differentiable at each point in the domain D is said to be analytic function. You can say a single valued function which is defined and differentiable at each point of a domain D is said to be analytic in that domain. Clear? Or in other words, you can say any function which satisfies CR conditions is called analytical function. CR conditions were del u by del x should be equal to minus del v by plus del v by del x del y, and del u by del y should be equal to minus del v by del x. These are your CR conditions. Clear? Let us define one more function, sometimes is called as a harmonic function. I'll tell you how the question are being asked, but let us first understand kind of questions sometimes. Harmonic function. Okay. Now if I say what was CR condition? CR condition says that del u by del x should be equal to del v by del y, and del u by del v should be equal to minus del v by del y should be equal to minus del v by del x. Right? Let us say we differentiate the first equation, differentiating equation 1 with respect to x, and equation 2 with respect to y. What will get? Left hand side will become del u by del x square is equals to del of del square v upon del x del y, and this side will get del square u upon del y square is equals to minus del square v upon del y del x. Right? Now let us say we call this equation number 3 and equation number 4. Now if I add equation 3 and 4, now adding equation 3 and 4, if I add equation 3 and 4, what I'm gonna get? I'm gonna get in the left hand side, it will become del square u upon del x square plus del square v upon del y square is equals to del square v upon del x del y minus del square v upon del y del x. Can I say this and this are the same thing? Yes, it does not make any difference, right? We already know when a multivariate function, this will not make a difference, right? For example, if I say del square v upon del x del y is equal to del square v upon del y del z, right? So this will not make any difference. So this part will become what? 0. So del square u upon del x square plus del square v upon del y square will be equal to 0. This is called as, you can also call it del square of is equal to 0. This is called as Laplacian equation. This is called as Laplacian equation, and u and v, keep a note here, u and v are called as harmonic function, are called as harmonic functions. Clear? Any function whose second derivative is coming out to be 0, sum of all second derivatives coming out to be 0 will come harmonic function. Clear? Now sometimes in gate papers he will ask you to form a analytic function. Maybe a real part is given to you, or imaginary part is given to you, and you to form a analytic function, right? So you can say forming a analytic function. Case 1 you can say, not case 1, in fact we'll consider both the cases. Forming an analytic function. Okay, let us consider case A. If real part is given, right, it is given to you x comma y is given, real part is ux comma y is given, right? See, we know that f dash z, what do we found? Del u by del x plus I times del v by del y, right? sorry, del v by del x, right? I think I have done this mistake in the writing the derivative also. Is it? No, we did it correct. Okay, right? So can I write this as, we don't know v, we know the only the real part. So del u by del x, using CR conditions, we can say it is minus del u by del y, isn't it? Right? So it all becomes in u, right? Now this is f dash z. We wanted what? Analytical function fz. So what we'll say is we'll integrate with or at point z comma 0. If we'll integrate this at point z comma 0, we'll get the answer. How? Let's understand this. Left hand side will become fz and this will become del u by del x, put z comma 0 in x comma y, minus iota times integration of del u by del y at z comma 0, plus you can say c. Very simply you'll get the answer. I'll tell you, we'll solve an example based on this. Second could be, if imaginary part is known to you. If imaginary part is known to us, that means v is given. Similarly, f dash z can also, when you know that it is del u by del x plus iota times del v by del x. So we know v now, change u. Del u by del x can be written as del v by del y plus iota times del v by del x. Very simply now we can substitute this particular value. Now we know the value of v now, right? So integrate, you will have to integrate to get fz, right? Integrate at point z comma 0, right? So again you will say left hand side will become fz, right hand side will be integration of del v by del y at z comma 0 plus iota times integration of del v by del x at z comma 0, right? Plus c you can say. Simply will get the answer. Correct? One more thing, sometimes he will ask you directly also. There is a second method, in fact. If real part is given to you, right? If real part is given to you, if u xy is known, a shortcut I'm giving you. If u xy is known, then f of z can be written as 2 times u of z by 2 comma z by 2 iota minus u00. I'll tell you how this directly in one liner you will get the answer. Right? Let's take an example, you'll understand it much better. This only for real part is known, right? Not imaginary part. Let us take an example. Find the analytic function. Find the analytic function of u is equals to x cube minus 3xy square plus 3x plus 1. Now u is given to you, analytic function fz is been asked to you, right? Let us solve it by both the approaches. First I'll show you the first approach. What is the first approach? You want del u by del x, which will be 3x square minus 3 into 2, sorry, del u by del x, right? So 3 into y square plus 3, right? And what will be del u by del y? Del u by del y will become minus 6xy, right? You know that f dash z will be nothing but del u by del x minus iota times del u by del y, as because we know the real part, right? So we can say that f dash z is nothing but, what did del u by del x? It is 3x square minus 3y square, is it? 3 square minus 3y square plus 3, and minus iota times it is minus 6xy, right? So you want to find out fz, so integrating both sides to get the analytic function. So fz is equals to integration of 3x square minus 3y square plus 3 at z comma 0 minus iota times integration of minus 6xy at z comma 0. So when it is z comma 0, so substitute that and then we will integrate it, right? So if I put z comma 0, so this will become integration of 3x square plus 3. I am putting z comma 0, right? X equal to z and y is equal to 0 minus iota times integration of 0, right? So this will become nothing but, no sorry, we will not put x here, this x will become z basically, and this is also 0. So this is basically 3 and z square integration will become z cube by 3 plus 3 of z integration plus, you can say, c iota. This gets cancels out, so it will become z cube plus 3z plus c iota. That is your fz, the analytical function which you are looking forward for. Correct? Now let us do the same thing or the same analysis with approach 2. What is the approach 2? I said direct shortcut. What was the shortcut? We said that fz is equals to u plus iota v, right? Where u is given to you is x cube minus 3xy square plus 3x plus 1. So you want fz. Fz is directly, I told you, is 2u of z by 2 comma z by 2 iota minus u 0 0. So find out u. So u z by 2 comma z by 2 iota. Directly what will become? Instead of x I will do z by 2, and instead of y I will keep z by 2 iota. So I'm substituting here. So this will become but z cube by 8 minus 3 z cube by 8 iota square plus 3z by 2 plus 1. Iota square is minus 1. So this can be written as z cube by 8 plus 3z cube by 8. So it will become 4z cube by 8 plus 3z by 2 plus 1, as iota square equal to minus 1, right? So, or you can also say u0 0. u0 0 is directly 1. So what will be fz? Fz will be z cube plus 3z plus 1 plus ci, right? Clear? So this is how we can actually get the analytic function back. Clear? The next part of this chapter is basically integration. Now we have talked about differentiation, let us also talk about integration. That is complex integration. Probably we will take this. Okay, let's take this particular thing. So complex integral, again we have to discuss called as something called as Cauchy theorem, right? We'll define something called as Cauchy's theorem. Cauchy was a person who did a lot of fundamental on analytic functions basically, or we can say complex functions. What does Cauchy's theorem said that if z is an analytic function, let us put it to the statement. If fz is analytic function on a simple closed curve C, then everywhere not then and on a simple closed curve C and inside the curve C, then integral of fz dz in closed curve will always be equal to 0, right? Then it will be always equal to 0. Clear? Now there is also a called as Cauchy integral formula, right? Let us discuss that about that also. What do I mean by that also? Cauchy integral formula. Now for a closed curve we have said it is will be 0, but if at any point you find the value of the function, if any at point, let's say this is a closed curve C, if you say in a closed curve it will be the integral will be 0, that integral will be 0, but at any point, let's say if fz is analytic function in the closed curve C, then let A be any point such that f of A such that f of A is nothing but 1 upon 2 pi integral fz upon z minus A dz. This can also be extended to nth derivative, right? If I say supposedly f dash of A will become 1 factorial upon 2 pi I into integral of f z upon z minus a the whole square. And if you extend it to nth derivative, it will become nothing but n factorial upon 2 pi I integral fz upon z minus a n plus 1. This again can be generalized, right? Now I'll tell you how examples are basically asked on this particular fundamental. Let us take an example. You'll say evaluate integral e raised to z upon z minus 2 where c represents a circle with mod z equal to 3. C represent mod z equal to 3. Mod z equal to 3 means radius is 3, right? And center is 0, 0, right? So let us say this is the diagram. This is basically mod z equal to 3, the circle, right? Mod z equal to 3. This is 3, 0. Now where is this point? A. This is A, right? The inside. Now A is inside in the closed curve. This will be how much? It is inside, right? So we can find out. Yes, we can find out f of A. So f of A was 1 upon 2 pi I integral fz upon z minus 2, right? So you want this value, so you want integral closed curve C fz upon z minus 2 will be nothing but f of 2 into 1 upon into 2 pi I, right? Now what is fz? If I compare fz is nothing but e raised to z, so f of 2 will be e raised to 2. So therefore integral fz upon z minus 2 will be nothing but e raised to 2 into 2 pi I. That's your answer, right? But if supposedly the question was asked something like this, if supposedly the question was asked evaluate integral closed curve e raised to z upon z minus 4 where C is a circle with mod z equal to 3. Now see, try to understand. Now in this case the circle is this and this point is here, so it is outside, so outside it will become what? 0. Inside only you can find some value, analytic functions inside, so this will be equal to 0. Clear? So this is how you can actually solve problems on these functions. You can try enormous number of problems on numerical integration, right? Cauchy integral theorem we can apply, right? Then there is one small subheadings which we can also discuss, that is called as residue theorem or points of singularity. Residue theorem, let's discuss that. Now before that we also discuss something called as singular points or singularity points. What are singularity points? Let us understand. See, in a closed curve C, everywhere you will not find that the function is analytic. There will be certain points where the function is not analytic, and that particular case will not neglect that function. We will say that we will find small point and we call it residue. So what is the residue theorem? The point where the function is not analytical is called as singularity point. So in a function, let's say there are certain points. Let's say this point, and this point. These 3 points, the function is not analytic. Otherwise, it is all analytic in this closed curve. So these 3 points will be called as singularity points, S1, S2, S3. Right? So we can write down points at which the given complex function is not analytic are called as singularity points are called as singularity points. Right? Now we can actually find the residue there. We will not be able to find the exact value. We can also find the residue. So what is the statement of residue theorem? You can say statement of residue theorem. What is it saying? Let us understand this. He's saying if fz is analytic in and on the closed curve C, except, not expect, I have written wrong spelling here. Expect is something which you will do after your GATE exam. Except at a finite number of singular points within C, within so if fz is analytic in an or closed curve C except at the finite number of singular point within C, then according to residue theorem, fz dz will be equal to 2 pi I times sum of residues at the singular point within C. This is what is the statement of residue theorem basically. Now how to calculate the residue? Very important for you to understand. How will calculate the residues, right? Calculation of residue. Residues can be calculated very easily. I mean, it is basically when you have a simple pole. When we have a simple pole. Simple pole is degree 1, you know, at z equal to a, let's say. Then residue of f of a is nothing but limit z tends to a, z minus a times fz, simply, right? For example, if you are given that there is a function, you have to find the residue of a function, let's say z plus 2 upon z minus 3, right, into, let's say, z plus 4. So find residue at z equal to 3. Z equal to 3 will be a point of singularity, right? So at z equal to 3, so that this will be nothing but residue of f of 3 will be nothing but limit z tends to 3, z minus 3 into z plus 2 upon z minus 3 into z plus 4. So this gets cancels out. So if you apply the limit, it will become 5 by 7. Right? So that will become the residue. Very simply, we can calculate the residue. Clear? So this is how basically you have to find the residues. Now you can easily try the questions on this particular fundamental and get the residue and the residue theorem. This is the end of